Okay, so picture this. A bolt of lightning squeezed into a wire thinner than a human hair.
Wow.
That's exactly what scientists did. They sent 2 million amps per square centimeter down a superconductor.
Really? 2 million?
2 million. It's millions of times more current than the wiring in your house can handle.
That's mind-blowing.
It is. And that's actually what we're going to explore today.
How cool.
Mega amps.
Mega amps.
How we generate and use these incredibly high currents.
Sounds intense.
We're your AI experts, and we're going to break it all down.
All right, so to even get to mega amps, we first need to understand how we create and control electric current in general, right?
Yeah, because we can't just plug into a mega amp outlet. So how do we generate these super powerful currents?
Well, you got to start with understanding current sources. Think of them like the opposite of a battery.
Opposite of battery, how so?
So a battery gives you a constant voltage, but a current source. It aims to deliver a constant current no matter the resistance.
Okay, that makes sense, but I'm guessing it's not as easy as just flipping a switch and boom, mega amps, right?
Exactly. Real-world current sources have some limitations, like internal resistance that can affect their performance, and also a compliance voltage, which is the maximum voltage they can handle. And when you're dealing with mega amps, those limitations, they become even more crucial.
So what kind of current sources can handle these massive currents?
Well, the simplest type is called passive current sources.
Passive current sources.
But they're not super efficient. You basically take a voltage source and combine it with a big resistor, and that kind of creates a constant current. But you waste a lot of energy as heat.
Ah, so it's like trying to control a fire hose with a garden sprinkler.
Yeah, exactly. So for a more sophisticated approach, you use active current sources. These use transistors to regulate the current flow much more precisely.
Okay, I see.
For example, there's the LM317 voltage regulator. It's this really versatile chip that can actually provide a constant current even to loads that are connected to ground.
So it's kind of like having a smart valve that adjusts itself to keep a steady flow even when the pressure changes.
That's a great analogy. And it's super important when you're working with megaamps because any sudden changes in current can be dangerous.
Yeah, we're not just talking about blown fuses here, so we've got these active current sources that can handle serious power.
Right.
But how do we actually use these mega amps in the real world?
Well, one fascinating example is the homopolar motor.
The what?
The homopolar motor. It was actually the first electric motor ever built.
Oh, wow.
Back in 1821.
So older than the light bulb.
It's surprisingly simple, too. Just a magnet, a wire, and a battery.
Wow.
What's remarkable is that this simple setup can handle enormous currents, and that's why homopolar motors are still used today.
Oh, really?
Yeah, like in railguns,
Really?
where you need that massive surge of energy to launch things at incredible speeds.
Oh, wow. Okay, now that sounds like science fiction. Mega amps launching projectiles.
It does, right?
Right.
But it really shows how harnessing mega amps isn't just about brute force, it's also about precision and control.
Right.
Exactly.
So we've got these powerful current sources and these incredible motors, but how do we take it even further? How do we reach those crazy currents like the 2 million amps we were talking about earlier?
That's where things get really exciting. And to understand that, we need to talk about superconductivity.
Superconductivity. All right, bring it on. I know it has something to do with zero resistance, which sounds like a total game changer for electricity.
It completely is. Superconductors are materials that below a certain temperature have absolutely no electrical resistance.
Meaning?
They can carry huge amounts of current without losing any energy to heat.
Wow, so no more wasted energy. That's incredible.
Exactly. And this zero resistance property opens up so many possibilities for high current applications.
All right, this is where things get really interesting.
Think about powerful electromagnets for MRI machines or particle accelerators that smash atoms, and even fusion research trying to create clean energy. All of these rely on superconductivity, and we're really just starting to understand what's possible.
Yeah, and the future of high current applications with superconductivity, even more exciting.
Okay, now I'm really interested. What's on the horizon? What kind of things can we expect to see in the coming years?
Well, for one, imagine a power grid that can transmit electricity with basically no loss. That's the whole idea behind superconducting power cables. They could totally change how we get energy, making our grids way more efficient and sustainable.
That would be amazing. No more worrying about wasting energy during transmission. What else?
Another big area is energy storage. Superconducting magnetic energy storage, or SMES, could be a way to store huge amounts of energy with almost no loss over time.
So no more batteries that slowly drain. That's incredible. Are there other applications too?
Oh yeah, definitely. Think about high-speed transportation, like maglev trains. They already use superconducting magnets to levitate, but with even more advances in superconductor technology, they could be even faster and way more efficient. It sounds like science fiction.
It kind of does, right? And then there's quantum computing. Superconductors are a key part of building these super powerful computers that could revolutionize everything from medicine to material science.
Quantum computers.
Yeah.
That's a whole other topic we could talk about. We've talked about making megaamps and even using them. But how do scientists measure these huge currents? It's not like they could just grab a multimeter off the shelf, right?
You're right. It's a great question, and it shows another cool thing about working with megaamps. To measure them, you need special techniques and equipment.
Okay, so what kind of tools are we talking about? Give us a sneak peek.
Well, one common way is to use something called a Rogowski coil.
A Rogowski coil.
Yeah, basically it's a flexible coil of wire that you can wrap around a conductor.
Okay, and how does that help measure the current?
So when the current flows through the conductor, it creates a magnetic field around it, right? The Rogowski coil senses that changing magnetic field and makes a small voltage that's proportional to the current.
Ah, so it's like using the current's own magnetic fingerprint to measure it. That's clever.
It is, and it's really useful for measuring those high-frequency currents that you see a lot in megaamp applications.
But before we wrap up, I have to ask, are there any downsides or risks to working with such high currents? Safety has to be a big concern, right?
You're absolutely right. Dealing with megaamps is serious business. The energies involved are massive, and any mistake could be disastrous. Safety is super important when working with these powerful currents.
It's like taming a powerful beast. You need expertise and respect and a lot of caution.
Exactly. And even with all the safety measures, there's always some risk, just like with any new technology.
That's true. Progress isn't always easy or risk-free. But it's amazing to see how we can overcome those challenges and make these incredible breakthroughs.
Definitely. And as we keep learning about superconductivity and develop new ways to control and use megaamps, I think we can expect even more exciting advancements in the future.
It makes you wonder what the future holds. Will we ever have room temperature superconductors? Would that make these technologies more accessible and more common?
That's the ultimate goal in superconductivity research. Room temperature superconductivity would be revolutionary. Imagine superconducting devices in our everyday electronics. It would change everything from our smartphones to transportation.
Wow, that's mind-blowing.
Yeah.
But even if room temperature superconductivity is still a long way off, the progress we've made with high current technologies is still pretty amazing.
I agree. From those simple homopolar motors to the cutting-edge superconducting applications we have now, it's been an incredible journey of discovery and innovation.
So what does all of this mean for everyone watching? What's the main takeaway?
I think the biggest takeaway is that the world of electricity is full of wonder, and potential megaamps might seem like a very specific topic, but they're actually a big part of many technologies that are shaping our future, like clean energy and advanced medical imaging.
This video has definitely made me appreciate the power and potential of megaamps.
I hope so. And if you're interested in learning more about the basics of electricity and how these technologies actually work, you should check out our Electronics Fundamentals playlist. It's a great place to start if you want to learn more about this topic.
And of course, don't forget to subscribe to our channel for more content like this. We're always exploring new topics and breaking down complex ideas so they're fun and easy to understand.
We want to make knowledge accessible and engaging for everyone, and we're so glad you're here with us.
We'd also love to hear what you thought of today's discussion. What surprised you? What questions do you still have? Let us know in the comments, and let's keep talking about it.
All right, that's it for today's video on mega amps. Thanks for watching, and we'll see you in the next one.